All right, let's try this again. This is take 2 for those of you who don't know. And you probably never will because I just deleted the other video because content that cannot be on YouTube. Anyways. So what we have here, what we're going to be talking about today, is some chemistry. And the reason why when somebody tells me that, you need to be brushing your teeth with fluoride toothpaste, I lose my shit. And when somebody tells me that fluoride is good for you to be drinking in the water, I lose my shit because it is absolutely horrid for you. It leaches calcium out of your bloodstream. It leaches sodium out of your bloodstream. It leaches chlorine and sodium ions out of your nerves. And it makes it nearly impossible for you to readily absorb iron. A lot of folks don't realize this, but this is why it's so toxic to you. Your body is not made to take on fluoride or fluorine or any kind of fluorine-based anything. Your body is not built for it. We use chlorine to do what fluoride does, chemically speaking. That's why you need sodium chloride. Good old-fashioned table salt, sea salt, same shit. Sodium chloride. Now this has a little bit of extras to it. Naturally occurring iodine, calcium silicate, and potassium iodide. Just a little bit of extras in it. But this is, for all intents and purposes, it's sodium chloride. Okay? So, especially for the intent and purpose of this video. We're going to discuss today the differences between a salt, a mineral-based salt, and a mineral. Okay? So, a salt is a gas that has been turned to a solid. Let me repeat that so that we can get through the actual general description of a salt. It is a gas that has been reduced to a solid state, whether that be chemically, that be physically, that be how, pick your poison. How you make that gas become a solid is how it becomes a salt. So, for instance, sodium fluoride, which is extremely toxic. There's a better one. Ferric fluoride, also known as stannous fluoride, which is what you use in toothpaste. It's also actually incredibly freaking toxic if you swallow it. That's why you're told not to use more than a pea-size amount on your toothbrush and not to allow a child to swallow anything when it comes down to brushing their teeth. Because stannous fluoride is actually very toxic to your body. It makes it difficult for you to absorb iron. A lot of folks don't realize this is what causes anemia. But anyways, I digress. My brain, it's scattery because I've forgotten, again, more things than most people will learn in their entire lives because they refuse to actually learn. They just want to go off of what other people say. So since you all are going off of what other people say, let's walk through the chemistry. Sodium chloride, that is a salt and a mineral that has been bonded to create a mineral salt. Ferric fluoride, that is iron, a mineral, and fluoride, which is a salt made from oxygen and fluorine gas. Those gases together create the salt. through chemical reaction. Then those in turn with the catalyst of the mineral create a mineral salt. And this mineral salt is then toxic to your body because you use iron, you use oxygen, but you don't use fluorine. And your body has to be able to use all the different atoms. So, in this chemical soup that makes up your body, using the wrong chemicals can actually be very bad for you. In turn, using the right chemicals is absolutely necessary for your health and your overall vitality. This is why humans have utilized sea salt for thousands of years in order to season their foods, but also as a supplement mineral intake, because it is a mineral salt. Again, salt is not that way because it's salty, because of the taste of it, the brackish bitterness. A salt, according to chemistry, is a gas in a solid form. In other words, dry ice is the salt, the physical salt, mind you. There's two different kinds. There's the chemical salt and the physical salt. Physical salts are compressed to the point of being a solid. Chemical salts are bonded to the point of being a solid. Okay? And again, a chemical salt is a gas bonded with another gas, which creates a solid. Mineral salts are a mineral and a chemical salt, which has been bonded. So, sodium chloride takes a chloride atom, which is 3 chlorines and 1 oxygen that are bonded, and then that bonds that to the sodium. And this makes sodium chloride. Just like a lot of different chemicals out there that you find. Okay, they're salts, minerals, gases. And a lot of the time when it comes down to chemistry, you'll hear somebody say the word solvent. I'm going to show you what a solvent looks like. There you go. That was a solvent. The atmosphere around you is a solvent. Gases are solvents. So are liquids. Liquids are just a different type of salt. Don't know if you knew that, by the way. All liquids are a type of salt, according to chemistry. According to physics, a liquid is a liquid, a solid is a solid, a gas is a gas. You get that whole idea. But according to chemistry, which physics is the reason why we have chemistry, you have a salt, you have a solvent, and you have a liquid all at the same time. Water. That is a solvent, a salt, and a liquid all at the same time. 2 gaseous atoms, another gaseous atom bonded. It's a salt. It is a chemical salt. Whether or not you recognize this, you've been this far into chemistry and understand this, that is your problem. If you're refusing to pay attention in school, you will never understand what I'm saying. And this is why I'm just adamant about people learning their chemistry, learning their physics, learning their history, learning about every little aspect that they learn in school, because you're going to use it in life. And if you think you're not, if you think that, oh, well, I'll never use it in life, so why learn it? I'm going to show you why that's wrong. In fact, I'm going to give you a little bit of an anecdote from my life where I thought, oh, well, I'll never use this. Me, personally, the freaking nerd who loves to learn, okay? I wasn't always that way. When I was in about second to third grade, I thought, Jazelbees. Okay. Anyways, when I was in second to third grade, wires, I thought, what am I going to do? What am I going to use this for? What this was division. What am I going to use division for in everyday life? What am I going to use multiplication for in everyday life? Well, if you buy groceries, you use multiplication and division. So, you may not be using it now in school, but you're going to be using it later. That's what my dad failed to tell me. Here's the thing. This is why I say learn everything you can in school. Learn everything you can out of school. Take all of that knowledge, bombard it against itself, and what falls out in a way leave behind. But what sticks, what you find out to be truth and real, hold on to, because it's very important and it will probably be used in your life. One of the reasons why I like history so much. I mean, I carry this right in my front chest pocket. For those of you who don't know what this is, I'm just going to hold it up to the camera for you so you can see. A freaking cell phone. There you go. Constitution of the United States, where I live. A little bit better angle here. Thank you very much for being a pain in my ass. Oh, I hate filming on a potato, but what can I say? I don't have the tower computer and the funds and extras and all that extra fun stuff and the thousands and thousands and thousands and thousands of dollars in cameras to be able to do things that would make it so that you could see without a shadow of doubt that what I'm saying is absolutely true. I can't sit there, y'all, and use an electromagnetic or super fire and electron scope to be, or microscope to be able to point out to you this particular atom and that particular atom differ by size. So if we look at them right this way, that way, we can tell that this atom is this many electrons, which means that it has this many protons, which means that it is this particular atom, and then this atom has this many electrons, protons, whatnot, and so it's this atom. I can't do that for you. I wish I could. This is why when we're talking about, schooling and whatnot, you do it on a piece of paper. You write it out. As a matter of factly, where's a good piece of paper for me to do this with? I'm gonna actually do a little written out diagram for you to see whatnot. Be right back. All right, so I'm going to draw you all out a little diagram here. We're going to have our sodium atom. This is our bonding measure. Okay, the sodium chloride. Oh wait, that's wrong. That's not our proper bonding measure. That would be yes. Okay, that's right. So that's and we go here and we go our chloride atom, which is one. They're all soft bonded. Wait, no, that's wrong. Because there's one that is right. Okay. And then we have our oxygen. Chlorine. Okay. And then, okay, so this is your basic structure of salt, table salt, right there. Let's see if I can get better framing you. All right, there we go. I can't draw backwards, so you're going to have to just deal with it in the way that the camera picks it up. So anyways, here we have our sodium atom, which is double bonded to our chloride atom. A chloride atom has one double bonded chlorine and two single bonded chlorine atoms with one oxygen atom in the central. This makes it so that, you know, the chemical itself adheres to itself. Okay. Now, normally the double bonded is the one that is opposing from the other double bonded. So just things to keep in mind. This being said, this is your basic sodium chloride. So now I'm going to go ahead and I'm going to write out fluoride. This is a fluoride atom. Okay. Or sorry, a fluoride molecule. Fluoride molecule. You'll notice a difference in the fluoride molecule from the chloride molecule shortly here. So, okay. So here we go. Here is your fluoride molecule. Y'all see this right quick? Now let's go ahead and go back to the chloride molecule real quick so that we can go ahead one more time and see what a chloride molecule looks like. And we're going to disregard our sodium for a second. That is our chloride molecule. All right. Do we see a difference here? One of those chlorine is double bonded to the oxygen, whereas fluoride, on the other hand, is not, which allows for free radical fluorine. One of the many reasons why it's so toxic. Now, what most people don't understand is that a fluoride molecule is extremely reactive, just like a chloride molecule, just like a bromide molecule. Any of these ide molecules are extremely reactive. They're willing to go and bond with other things. Okay, I give you bromine and chlorine, not so much, but you know, the ide molecules, the IE or IDE molecules are more reactive, you know, more willing to go and play around with other chemicals than other chemicals really are. This is why fluoride is useful to an extent. Useful to an extent when it comes to mineral salts. Making those mineral salts, the usability of those mineral salts in certain industrial applications. There again, though, they are not biological applications. They are industrial applications. There's a difference here. So anyways, so we're going to have our calcium atom here. Okay. Calcium, if I remember correctly, was 15. No, that's potassium. I need my freaking periodic table sitting in front of me to be able to sit there and be able to go, okay, this, that, it did it reference this, that, and the other. Okay, but just bear with me. So we got our chloride atom, our fluoride atom and calcium atom here, represented by this circle and our fluoride. Okay. Now, when the calcium atom, which is just, it likes to stick to gases, it just likes it a lot. So when we take that calcium atom and we bond it with our fluorine atom in order to get the fluoride, calcium fluoride, which you don't realize this, but this is what fluorine does, or fluoride does in your body. It bonds to the calcium in your body most readily, but it also bonds to iron. It bonds to sodium. It bonds to potassium. It bonds to magnesium. It bonds to every mineral in your body, which is really freaking bad for you, but I digress. So when we bond these, okay, you'll notice something here. This is what happens in that chemical bond. So now you've got your calcium, and it is triple bonded, which triple bonding means that it is not readily able to be removed from that chemical now. It is part of it. It's solidly part of it. So you've got your triple bonded calcium atom to a double bonded fluorine atom to a single bonded fluorate, which is two fluorine and one oxygen. A fluorate. Okay? So now that we've gone over that stuff, you can kind of see why fluorine isn't necessarily good for your body, because it wants to bond with those minerals, those mineral salts and minerals and whatnot in your body, in your bloodstream, that you would normally need to stay there. It bonds so well with it, in fact, that it has the ability to rip it away from the rest of your body. And now it's free floating around in your system, not being able to be used because it's attached to a fluoride atom. And your body can't use fluoride. Literally can't. It does. There's nothing for the fluoride to do except for to rip away calcium and rip away magnesium most readily, but also sodium, iron, phosphorus. I can go on and on and on. Fluorine is one of the most reactive gases known to mankind. In fact, it's been speculated to be the most reactive gas known to mankind. More so than oxygen. And in this case, y'all, I want to point out this is how fluorine can cause you to have fluoride poisoning. You have calcium in your nerves that helps with things like memory and synapse timing and conductivity of your nerves. It allows the electricity to flow through them. Fluoride disrupts that by bonding to the calcium and making it so it's not available for other activities and other chemical processes. This is the difference here between I brush my teeth with fluoride toothpaste and I brush my teeth with freaking Listerine and nothing else. I won't even deal with the Burt's Bees crap. I won't even use sodium bicarbonate because you can overwhelm your sodium levels. You get the calcium and the sodium you need from the salts in your diet. You don't need to be going and sitting there and shoving freaking chemical poisons into your system that literally leach it out of your system and make you pee it out later, if you're lucky. If you're lucky, you'll pee it out or you'll sweat it out. Otherwise, remember, now we've got a fluorate on this particular, right? You got your one triple bonded calcium to your double bonded fluorine. Then you've got your fluorate. Well, these two are readily available to react. And let's say we take an iron atom, okay? We're going to take and put an iron here. So there's our iron atom. And what ends up happening with an iron atom is due to its specific charge, it double bonds with the fluorine atom and breaks the fluorate. So now you've got your iron fluoride. Your iron fluorine. And this turns into, because it will now readily bond with just about any gaseous substance out there, it will readily bond with chlorine, it will readily bond with oxygen, it will readily bond with a whole bunch of different stuff. And it's not usable by your body, because once it bonds with that atom, with that fluorine atom, that triple bonds the iron and the fluorine to whatever you are bonding it to. Again, your chain of bondage, your chain of chemical bond. All right? This comes down to electron charge. This is why this is important. You say, for instance, we'll just go with a simple one. Hydrogen has one electron. Okay? One proton and one neutron. One proton and one neutron down in the middle. So you've got your electron, proton, and neutron. Say we want to bond this hydrogen with something, like, for instance, carbon. Well, carbon has a certain outline here. We have 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, 5, 6. Okay, there's your carbon nucleus. Doing a little bit of quick for you. And then we've got our carbon electrons. Got one here, one here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, okay. So here's your carbon atom. Now, you'll notice in this outer shell there are 2 electrons, and in this shell there is only 1 electron. Hydrogen will bond with carbon because there is this space here.